Today we're going to finish section 3.5. We had looked at some multiplication algorithms last time, and we looked at the standard algorithm for division, and we talked about the fact that it's a little bit confusing, but more than anything, it just flat out hinges on you knowing the multiplication tables for whatever you're dividing by. And if it's a small digit, we're all probably pretty okay with that. If the number gets large enough, like if you're dividing by 17, I don't know my 17s tables, and it makes it a little bit more difficult. And then we also talked about the fact that there are children with special needs that can't always do the memorization thing. Does that mean then they have no chance, aside from a cheat sheet, of being able to divide? And the answer, of course, is no. So I want to show you the repeated subtraction algorithm. Now, you might remember we talked about repeated subtraction before, or at least that phrase should ring a bell. We saw it back in section 3.3. And we talked about handing out rocks or something like that, and we went down the line and we handed them out to all 6 people, and we put -6, and we figured out, oh look, I have 18 rocks left. Shake your head if you know kind of what I'm talking about. Okay, good. All right, so that sounds all well and good, but if you had 623 to subtract 5, like 5 and 5 and 5, that would take forever. Are you with me? So there is a modification for what happens when the numbers are further apart, right? If I don't want to actually subtract 5, what would I do? And here's what this looks like. Okay, so we're going to take 623, and I said 23 and I wrote 33. Let's try that again. And we're dividing by 5, and what we do is we subtract the 5 from the biggest number that it subtracts from. So for instance, the 6 in the hundreds place, I could subtract a 5 from that 6, right? But if I did, I wouldn't really be subtracting 5, I'd be subtracting 500 because I'm subtracting it from the hundreds place. And what I do when I do that is I've actually multiplied 5 times 100 because there's 5 hundreds there. Does that make sense? That's way better than subtracting 5, isn't it? Oh yeah. And when I do that, I end up with 123. Now, I can't subtract a 5 from the 100s column now, right? The 100, it won't work. But I could subtract it from the tens column, yeah? I mean, I know 2 minus 5 doesn't work, but if I think of this as 12, I meant to do a different color, 12 minus 5, it'll be okay, yeah? So what is 12? Well, first, let me write my 0 here. Come on, so this is 5 times 10 to subtract actually 50. So what is 12 minus 5? That's 7, so now I have 73. Could I subtract again in the tens column? Yeah, I could, right? I could subtract another 50, which is another 5 times 10. And if I do that, I end up with 23. Could I subtract 50 again? No. So now I'm back to subtracting a single 5 because I don't have anything else I can do. 23 minus 5 would be about 18. This is 5 times 1 when we do this. I'm going to shrink my work just so that I can continue it on the same line. You can obviously continue into another column if you need to, but... Okay, can I subtract 5 again? I can. So what is 18 minus 5? 13. May I subtract 5 again? Yep, and I'll get 8. And each time I'm doing this, I'm subtracting 5. It's 5 times 1. And I can do it one more time, leaving me with a 3. I can't get the 3 quite in there, but you know it's there. And 3 is too small to subtract 5 from, right? And still stick with whole numbers. So here's the cool thing. The answer is over here, 124. And I have a remainder at the bottom of 3. The only thing you ever subtract is the number you're dividing by, or that number with zeros on the end. So if I were dividing by 17, I'd subtract 17, or 170, or 1,700, or 17,000. Are you with me? And that's what makes this method so friendly. Now, on the flip side, when is it not friendly? Well, if I had to do this 9 times, right? If when you actually divided, you got 19, and I had to subtract the 5 off 9 times at the end, that's not super friendly. I understand that. It's at least not super efficient. But it does work, and it doesn't rely on you having to know any multiplication tables to do it. Okay? All right, so what we're going to do next is we're going to do a few word problems. And as we do the word problems, we're going to employ these different methods from last time. Some of them we haven't talked about yet again today, but we will, as well as standard algorithms. Maybe when we throw them in there occasionally, that's fine too. But just to try to remind you of some of the other methods. So here's an example. Juan saved $5,340 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? So there's lots of steps to this problem. You are not going to just be able to do one thing and be done. So what do you think you might try to do first, or what do you see as being a valuable thing to do first in this problem? Michaela, you're about to talk to me.
Even if it's like, so are we using our own method or are we using these?
Okay, so let's not talk about methods. Let's just talk about what operation we're doing on what numbers first.
So 95 times 12.
Okay, and so you can tell me, why are we multiplying 95 times 12?
Because there is 12 months in a year.
12 months in a year, and I've saved $95 per month. So you're attempting in this operation to find out how much he saved in year one, right? Okay, does that make sense to everyone? Okay. So we're going to use some other method to do this, just to remind ourselves of one. So I don't know which one. Every time I do it, I do something different that's in my notes. So we're going to do partial products. So 90 and 5, and then we're going to have 10 and 2. Okay, and what we do, that's not going to work, is we create a box, and we divide our box, since these are 2-digit numbers, into a 2x2 grid. And we multiply row by column. So in this row and column, we would multiply the 90 and the 10. Okay, so what is 90 times 10? 900. And then in this row and column, we would multiply 5 times 10 to give me 50. In the first row, second column, I'd have 90 times 2 to give me 180. And then the last one is 2 times 5, so I have 10. And then we're wanting to add these up. So I have 900 plus 180, 50, and 10. What am I going to get? Somebody have it yet? Yeah, it's 1,140. Okay. So I have 1,140. So this is step one. You know, I found out how much I saved in year one. Now what? So, sounds good. So I have 5,340. And I'm subtracting 1,140. This is a really nice subtraction because there isn't any borrowing going on or anything, so it's very friendly. And I end up with 4,200. Okay? 4,200. There's a couple different things I could do now, so somebody give me a suggestion of what you see. Could divide by 24. Okay, so 24 is a really good example of a number that I don't know multiplication digits, multiplication tables for 24. I could get a little ways just from what I know about 12s, right, because it's doubling it. But too far along, I'm not going to do very well. So let's do repeated subtraction just to give ourselves a chance to practice that. So I could subtract the 24 here, right? And this would be 24 times what? 100, because there's 2 zeros I've put on the end, right? So what is 4,200 minus 2,400? It is 1,800. Good. May I subtract 2,400 again? No, I can't. But I can subtract 240, right? A 24 times 10. And hopefully you're looking at that and you're like, I'm going to subtract several 240s, right? There's going to be quite a few of them, and there are. So the first one here would be 1,560. And then I need another 240. I don't have this written down, so you guys are going to have to tell me if I make a mistake. What's the next one?
1320.
1320. And every time you're doing it, you're writing down what you're actually subtracting it, because we're going to use those to add them up at the end, right? So I've written down 24 times 10 3 times so far. Let's see. This would be, is it 1080? Okay, 240. 840. It's another 24 times 10. I'm at 600. Okay. All right, 600 minus another 240, right? 360 minus a 240. It's 120. All right, can't subtract 240 anymore, so now what will I subtract? 24. So 96. So this is 24 times 1. 24 again would give me 72. 24 again. 48. We're getting really close. 24 again. And again, and then we're at 0. All right. I'm going to give you another thought on how to do this problem when you're done too, just so that you can see another way of thinking about it. Our answer's here though. It's 100, 10, 20, 30, 40, 50, 60, 70, 170, 1, 2, 3, 4, 5. 175. $175 per month. Okay, so Katie, you told me to divide by 24, and it totally works. And where did you get the 24?
How many months over the last 2 years?
How many months are over the last 2 years? Definitely one way to do it. Another way that we could have done it is we could have divided by 2 to find out how much we got per year, and then divided by 12. And we might have had fewer steps. I haven't done it that way on my paper, so I'm not sure that that will be fewer steps, but it's another possibility. So there's lots of different ways to sort of process and think through our problem. And we're always going to get the answer, $175. Okay? There are some occasions, I'm pretty sure I mentioned this last time, but just let me reiterate it again, where your book's going to tell you what method to use. Okay, flat out going to tell you. And there's going to be some places where it's not going to tell you. But under no circumstances is a plug it in the calculator with no work an acceptable method, all right? It's kind of like we don't give the 3rd and 4th graders who are learning to do the division the calculators just yet. You don't get to use the calculator. You can to check, but to show your work, you have to actually show division. So even if it doesn't look like repeated subtraction, it could certainly look like the standard division algorithm, that kind of stuff. Does that make sense? Okay. All right, let's try another one. We've got Dan. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as in the third box, and there are twice as many in the second box as the first box. How much money does he have in each box? So, what might you do to start solving this problem? This is almost like going back to the problem-solving stuff from chapter 1. I personally would draw 3 boxes. Are you good with that first step? Okay. So here's our box 1, 2, and 3. It references that there are 3 times as many pennies in the first box as in the third. So we don't know how many are in the third box, but one way to do that would be to just let it represent a variable quantity. If you were working with children before we got to variables, you're going to do a lot of guess and check probably with this particular problem. But no matter what happens in box 3, how much do you have by comparison to box 1? 3 times as many. So if you were working with kids where you're doing guess and check and you were like, okay, box 3 has, let's pretend, 1,000 pennies in it. Is that reasonable for a number? Sure. 1,000 pennies in it. So if it has 1,000 pennies, how much would be in box 1? 3,000, okay? All right, cool. So let's take a look then at box 2. How does box 2 compare to the other boxes? Twice as many as the first box. So the first box has 3x, so our second box has 6x. Yeah, 2 times the 3x or 6x. And again, if you were using my example from before where we said 1,000 pennies and then 3,000 pennies, that would make 6,000 pennies in the middle, and that's too many pennies. And we would have to adjust our guesses, right? Down, because that's too many. All right, it says, though, that all the pennies added together are how many? 4,520 or 4,520. So we can take the 3 pennies, whether we're doing guess and check or we're doing, some algebra, which is what we've got written down at the moment, and add them together, and we've got to check to see do they equal 4,520. So in my example where I had 1,000, 3,000, and 6,000, they don't equal 4,520. Now I've got to go back and say, okay, maybe that's too high of a guess. Maybe I start with 500. 500, 1,500, and then 3,000. Does that work? Oh, no, it's still too high, and I keep guessing, right? Okay, so with a little bit of algebra, we can avoid some of the guessing going on, and I have 3 plus 6 plus 1 is how many? 10x equals 4,520. So what would I do then? I divide by 10. So on this one, the division is so friendly, right? Because there's the zeros at the end. Please, you can't cancel out anything but zeros like that. Don't do that, okay? Just the zeros. Right? Just dividing by zeros. I had somebody do it on a test once in this class.
Don't X out the egg.
You can do the zeros, but I had somebody do this. Yeah, I had somebody do that on a test. You can't do that, okay? It only works because it's 0, so don't do that. Oops, yeah, that's all I was saying. Okay, very good. 4,520 divided by 10 would be 452. My second guess of x equals 500 was actually pretty close, wasn't it? When I did a guess and check step there just a minute ago. 452. But the question asks how much money, right? How much? You could write down you could write the word pennies if you want, or you can write dollar amounts. But how much money is in each box? So what does this 452 mean?
There's 452 pennies in box 3.
Yeah. So if you're doing it with whole numbers, like you're still working with kids who are working with whole numbers, your box 3, you could just say is 452 pennies. That would be fine. Or if you're comfortable at that point in working with dollar amounts and you want to put down that it's $4.52, that's fine too. What would I do next?
Check to see how many was in box 1 and box 2.
Right, we could go back to box 1 and box 3. So we can take that 452 and we would multiply it by 3. And if we do that, we will actually get, I'm going to do it in dollar amounts. In box 1, I have 1356. And, oops, let's just say box 1. And then in box 2, I have 27, I would double it again, right, from box 1, or just multiply by 6 from the other one would be 2712. Okay, everybody good? All right, let's take a look at another one. This one's interesting. A student observes that 39 plus 41 is equal to 40 plus 40. It's true, they are equal. But they want to know if 39 times 41 is equal to 40 times 40. How do you respond? Is it equal or is it not? No. Catalina, how did you decide that it wasn't equal?
Because when you multiply 40 times 40, you do like 4 times 4 is 16 and you add the 2 zeros, so it's 16.
Okay.
And you can't do that with 39 times 41.
Yeah.
It's going to be an even bigger.
Yeah, well, it's going to give you a 9 on the end. It can't be a 0 on the end, right?
Right.
Yeah, for sure. And the number it actually gives you, just so that you're aware, is 1599. So this question, we're going to flip the page here in a second, and it won't actually equal. But the first question, this first question is, are they equal? And the answer is no, they're not. And you could show students very quickly that they simply don't multiply out to be the same value. Now, the next question goes a little bit further. They're really close though, right? I mean, 1599 and 1600, really, really close. Agreed? They're exactly how far apart? 1. And so that's what's going on example 10. Another student observes that 39 times 41 is 40 times 40 minus 1. And 49 times 51 is actually 50 times 50 minus 1. And he wants to know if the pattern continues. Can you always do this? And if it does, what relationship has to happen between the first two values? How do they have to be connected, or in what relationship do they have to be between the first two numbers for this to happen? So how could we test to see if this pattern continues?
Use a different number that ends in 9, and then another number that's 2 away from it.
Okay, so maybe 19 and 21. Or maybe 59 and 61, right? That's what you're suggesting. Is that right, Colton?
Yeah.
Okay. So you're speculating by using these specific numbers that there's two conditions you held fast. One condition was that they were two numbers apart. You said that, right?
Mm-hmm.
And the other condition is that it ended in a 9 and then it ended in a 1. Those were the two conditions you're checking. So we might want to speculate that that's the case and see if this works. It will if we check this. So let's just check real quick. 20 times 20 is 400. So 400 minus 1 is 399. So grab your calculator, just check for me. Does in fact 19 times 21 equal 399? Did it work? Yeah, it does. All right, let's check this other one. So this would be 6, if it works, it's 60 times 60 minus 1. So 60 times 60 would be 3,600, right? Minus 1 would be 3,599. Is that what we get when we do 59 times 61? Okay. So at least if we hold those two conditions steady, it seems to be working, right? A part of the question needs to be, do both of those conditions have to hold? So what could we manipulate to see if there's actually a need for both those conditions? The two conditions, again, to remind you, were that it ended in a 9 and a 1, right? And that they were two numbers apart. So let's manipulate with the two numbers apart first. Let's try that. Let's say, for instance, that it did, or 4 numbers apart instead. So let's say you did, we'll start with small numbers. What if it's 18 and 22? Right, they're 4 numbers apart. Well, we know the right-hand side, because I just did it above, was 399. What is 18 times 22? 396. So this is no good, right? This condition does seem to need them to be closer together. Being 4 apart was too far apart. Are you with me? Being 4 apart was too far apart. What about it actually being a 9 and a 1, though? So let's try something else that's 2 numbers apart. So maybe you do 24 and 26. So it's 25. If it works, the number between is 25 times 25 minus 1. So 25 times 25 is 625 minus 1 would be 624. Is 26 times 24 624? It actually works. So the pattern does continue. And while it's really nice when it spans across the tens digit, right? We always love the tens because multiplying is so nice with those zeros on the end. It's not absolutely necessary. Nice, but not necessary. So this would work in general. As long as the values are 2 apart. Does that make sense? There's some algebra going on behind the scenes here of why this works. Let me just show you real quick, not because you would show this to a child, but because I don't want you to think that this is some sort of mystery of mathematics. It's really not a mystery at all. What's happening is that when we multiply a number and a number that's 2 less than it, we're trying to compare that to what happens when the numbers are the numbers the same, right? Minus 1. And if you did a little bit of algebra, this would be n squared minus 2n on the left. And on the right, when you FOIL or multiply this out, you would get n squared minus n plus 1 minus 1. And these two would add to 0. And you would be getting n squared minus 2n. So that's actually showing that it does, in fact, need them to be 2 apart with the number 1 in between to show that it actually works. Because we end up getting, in fact, the same thing on the left-hand side and on the right-hand side if they're 2 numbers apart. Just so that you're aware, it's not magic. All right, few mental math methods. So again, we've talked about mental math before. Mental math means you don't need to write it down, but you're going to just because that way I can see what's going on inside your head, right? Okay, so I want to show you some mental math methods. The first one is front-end multiplying, and I would like to put a caution on here because every now and then I have somebody who thinks that they can do 5-digit multiplication of something or other in their head with front-end multiplication, and you can't. I can't either. The little genius boy that shows up on one of these talk shows, sometimes he might be able to. You guys have probably seen those kinds of kids show up before, but we're talking about just the kids in your class, right? So this can only work for a few digits, okay? So you'll see here, this is a 2-digit number times a 1-digit number, right? So what am I talking about here? Well, we already talked about front-end multiplying before. The idea of front-end multiplying is taking the first 2 digits, in this case it's 40 times 5, and multiplying to give you 200. And then taking the 6 times 5 and multiplying to give you 30, and then adding the results. If it gets much bigger, there's too many things you have to remember in your head to make it work. Right? If I were doing a 4-digit number times a 1-digit number here, that's too much going on. I'd have to remember all 3 of the previous products plus the new product, and then I'd have to add them together. Too much going on. But when it's small, it works pretty nicely. I think that we probably could all remember the 200 while we found the 30 and then add those together pretty well. So this is called front-end multiplying. Compatible numbers is lots more helpful than non-compatible numbers. In particular, it would be super unhelpful to multiply 5 and 5 together. It's not the worst thing ever, right? 25 is not a terrible number. But man, isn't the number 10 better? It is. So you're trying to find numbers that are friendly to use. For example, you might choose 5 and 2 to give me 10, and you might choose 4 and 5 to give you 20, right? So now I've got 20, I've got 10, and I've got 5. And the order doesn't matter. Multiplication's commutative. So if you had 20 times 10, yes, ma'am?
Would it be 8?
I skipped my 8. I skipped it. Oh, you mean this 5 at the end. Sorry.
Yeah.
It's like,
Yeah.
I'm skipping over the 8. That's where you want that 8 to be. Yes, you're right. I want there to be an 8 there. Thank you. All right, so 20 times 10, also very friendly because you got lots of zeros, right? So what's 20 times 10? 200. And then 200 times 8 would be 1,600. And it's not horribly awful to multiply, hang on, the 8 and the 5. 40 wouldn't be bad. But 8 and 4, that'd be yucky. I don't want 32. I don't want to multiply with 32. That sounds terrible, and certainly not in my head. So there are certainly numbers that work nicer to multiply together first, and that's the compatible numbers strategy. This one is very clever, and everybody forgets it when it comes time to use it. And so I'd encourage you, it only works for some digits. Okay, I'm going to be honest with that. It only works for multiplication by 5s and by 25s. So it's very limited, I get that. But the idea in it is that we have a value of money that's worth 5 cents. It's called a nickel, right? So if I am thinking about this like money, this is equivalent to having in my pocket 46 nickels. Okay? 46 times 5, how much money do I have? It's 46 nickels. I mean, nickels aren't the worst thing ever, but dimes are way better. At least they are in terms of counting how much money I have. They're a lot easier to work with. So if I have 46 nickels and I turn my nickels into dimes, how many dimes would that be? 23 dimes. Now, the process that we did in general is that we multiplied this by 2 and we divided this by 2. You guys with me on that? And there's nothing special about 2. I mean, I could multiply by 3 and divide by 3. I could multiply by 7, divide by 7. I can do that with any number. But man, getting a 10 at the end is super friendly because what's 23 times 10? 230. So what I've done is I've, in my mind, exchanged 46 nickels for 23 dimes. Okay, so if I'm thinking money, what is this 25 representing? Quarters. This is a quarter. So I'm saying here that I have 44 quarters. There's got to be a better way to carry around my money than 44 quarters in my pocket. What would be friendlier? Dollars would be way friendlier. Even if it's dollar coins, it'd be friendlier, right? But definitely if it's dollar bills, it would be friendlier. So if I have 44 quarters, how many dollar bills is that? 11. Yeah, so what we're doing is we're multiplying this number by 4 and we're dividing this number by 4. 25 times 4 is 100. It's a very friendly number. 100 equivalent to $1, which is worth 100 cents. And then the 44 divided by 4 would be 11. And then what's 11 times 100? 1100. Okay, 2 mental math methods for division, and then I've got a couple estimation ones to show you. Mental math for division, 6318 divided by 9. Well, this is, again, these things only work when they work. They don't work all the time, and I get that. But when they work, they're very nice to notice. 63 and 18 are multiples of 9, right? Yeah. So instead of thinking about this as 6318, we can think about this as 6300 and 18. So I'm just breaking 6318 into 6300 and 18, and I'm dividing by 9. Well, the 9 goes into 63 how many times? 7, so that's 700. And the 9 goes into the 18 twice, so this is 702. And it's really easy to identify on this one because the 63 right there, it's all right there. You see the number 63 and then everything zaps itself out. We're going to do the same thing on this one, but it doesn't look as obvious. Like I can't just break this into 42 and 5 or into 4 and 25. But I can break it into 4 and 25. It's just not obvious that I can. It's really 425, right? And 400 does divide by 5, even if I didn't notice that the 4 at the beginning by itself did. So what is 400 divided by 5? 80. And 25 divided by 5? 5. So I'm adding these results together, right? This is 85. Okay, let me show you 2 estimation strategies. They're similar to the strategies for mental math already. They just chop things off and make them easier to work with. I told you front-end estimation, if I told you front-end multiplying, is not so friendly when the numbers get big. In fact, a 2-digit number times a 1-digit number is about all that you can manage, at least if you're young. I mean, you guys can manage more, and I know that. But if you're working with children, that's about all you can actually manage to talk about in terms of mental math, right? So we're going to take the 386 times 4, and we're going to chop off, if you will, we're going to ignore the 6. I mean, I'm not changing it to 38, but to 380. So I'm going to ignore the 6, and I'm going to, in my mind, say that this is going to be approximately what happens when I have 380 times 4. Are you with me? okay? Because again, I'm now doing a 2-digit by 1-digit multiplication with some zeros on the end for some fun, you know, just because it's fun, okay? So I have 300 times 4, and I have 80 times 4. So what is 300 times 4? 1,200 or 1,200, right? And then what's 80 times 4? 320, yeah. That was 7, I think you were thinking. Yeah, 320. There we go. And then I would multiply, or not multiply, then I would add those two products together. So what is 1,200 plus 320? 1,520. And of course, that's not an exact answer, and I'm okay with that because the directions say that I'm supposed to be estimating. And I knew I wasn't going to get an exact answer when I ignored the 6 at the end, right? Absolutely. Compatible numbers. So compatible numbers mean numbers that work together nicely. 4132 is not exactly numbers that work together nicely, but it's close to what? What would? It's really close to 4,000. And you know what? I would love to divide. I would love to divide 4,000 by 4. Exactly. Wouldn't you? Yeah. What's 4,000 divided by 4?
1,000.
1,000. Yeah. So we're at 1,000. If you looked at that and you were like, oh, I didn't think to do 4,000. I thought to do 4,032 because 32 at the end automatically divides by 4 too. Totally cool. It's an estimation, right? And it would be fine. So if you're estimating and somebody else is estimating and you're getting answers that are very close, you're likely doing good stuff and it's okay. All right?